Physics. This is Unit 3, and we're going to be looking at magnetism and its relationship to electricity. For our first quiz, we're going to be exploring magnets in general and the concept and ideas of magnetic field and magnetic force.
You've probably had some experience with magnets, even if it's just the magnets that are stuck on your refrigerator. Notice that when I place these two magnets near each other, they push each other apart. Now, they actually accelerate away from each other, which indicates there's some kind of force here. This is a field force because the materials are not touching or contacting each other in order for the force to be applied. When I turn the magnets around, then we see that they are attracted to one another. In magnets, like poles repel and opposite poles attract. There are no monopoles. In other words, anytime you have a magnet, it must have a north and a south pole. If I break a magnet in half, each piece will have a north and south pole. But how do magnets work anyway? What causes this magnetic field? It all begins with individual atoms. We know that an atom has a center, proton and neutron nucleus, surrounded by electrons. Each of these negatively charged electrons has kind of a spin. They spin one direction or the other, either clockwise or counterclockwise. Moving charges, as we're going to see in this unit, create magnetic fields. And so an electron spinning is a moving charge. Now, in most elements, the electrons have opposite spins and it cancels each other out. But in some elements, the electrons do not cancel each other out and in fact sort of magnify one another with their spin, and this creates a magnetic field. Materials that are naturally magnetic are known as ferromagnetic, and these include iron, nickel, and cobalt. But if each individual atom is a magnet, then why aren't all pieces of iron magnets? That's because we have areas within that piece of iron known as domains. And in each of these little microscopic domains, the magnetic field is pointing in a different direction. And these different directions cancel each other out. Now, in materials like iron, this piece of iron could be exposed to a magnetic field, and all of those domains can then be aligned along the magnetic field of the magnet they were exposed to, making this piece of iron magnetic. Notice that all the domains have to be aligned in order for this piece of iron to be a magnet. Let's imagine that we have a wire that has a current I flowing through it. Remember that moving electrons create magnetic fields. So there must be a magnetic field surrounding this wire. But in what direction? In order to find that out, we use something called the right-hand rule. Take your right hand, take your thumb, and point it in the direction of the current. Your fingers indicate the direction of the current. In this case, your fingers indicate the direction of the magnetic field. Magnetic field is indicated by B and is measured in Tesla. For a current-carrying wire, the magnetic field surrounds the wire in a circular fashion. Let's imagine that we have a coil of wire with a current traveling through it. This is called a solenoid. What would the magnetic field look like for a solenoid? The field lines inside a solenoid point in the same direction and are nearly parallel. They're uniformly spaced and they're close together. So the magnetic field inside a solenoid is strong and nearly uniform. Solenoids are used in a lot of applications, and most of the appliances that you have in your home use these kinds of devices. One device that can be created with a solenoid is an electromagnet. An electromagnet is formed when a piece of iron is placed in a solenoid. Let's take a look at some of the problems that you'll encounter in the quiz. For your first problem, you're going to be looking at a length of wire that's carrying a current. In this particular case, we're going to be looking at a length of wire that's 10 meters in length and carrying a current of 3 amps, pointing in the positive X direction. We have a magnetic force that is 6.2 times 10 to the negative 5 newtons in the negative Y direction. And we need to find the magnitude and direction of the magnetic field that's producing this particular force. Our formula for the force, the magnetic force, is equal to the magnetic field strength times the current times the length of the wire. To rearrange this formula, we are going to divide both sides by current and length. We substitute our numbers and solve. And we get an answer of 2.07 Tesla. But what about the direction? We have to use the right-hand rule in order to solve for direction. The thumb points in the direction of the current, and the palm of the hand is in the negative Y direction. So you kind of have to turn your hand in a funny way to get that to happen. And then when you do that, you'll see that B is sticking out towards us, and that is in the Z direction. Each of these are perpendicular to each other. For our next problem, we have a proton that's moving perpendicularly in a magnetic field. Our magnetic field has a magnitude of 4.2 times 10 to the negative 3 Tesla. We're trying to find the speed of our proton if the magnitude of the magnetic force is 3.1 times 10 to the negative 14 newtons. Now remember that a proton has a charge of 1.6 times 10 to the negative 19. Our formula tells us that the magnetic field strength is equal to the magnetic force divided by the charge times the velocity. Rearranging, we get velocity is equal to force divided by field times charge. Substitute your numbers and solve. And we find that the velocity of our proton is 4.61 times 10 to the 7th meters per second.
You are now ready to take the first quiz for this unit. Please take it in the Google form provided in the teacher notes. Then you'll be ready to move on to the next video and we'll look at the second quiz. Good luck.